essentially, this is about two ideas that I currently find really exciting. On the one hand, Unikernels, and on the other hand, microservices. And as you'll see, there's going to be a gossiping protocol that's the enabler of combining these two approaches. And the reason I'm really into Unikernels right now is the security and performance benefits that they can offer compared to the traditional model of writing applications. So don't worry if you don't know much about Unikernels or microservices. I'm going to start out by giving a brief introduction to both before we dive into the details of writing microservices using unikernel technology. So very briefly about myself, my name's Andreas. I am on social media and GitHub, and I currently lead a team of engineers out of Copenhagen. You might know Zendesk for customer support software. All right, so to talk about microservices, I think it's good to contrast with the classic approach of having a monolith, and I'm going to try to describe my journey into microservices. So around 5 years ago, I joined an internet startup as the third backend engineer. They had a classic REST API, and the monolith was written by this quite brilliant engineer. And being a monolith, all the functionality was in a single process, as illustrated by these colored dots. And when you wanted more capacity for a single component, you would run more of the same process, right? And if one piece of functionality, let's say the pink, depended on the orange, then everything was just a function call away. It's pretty simple. On the other hand, the boundaries between the components were maybe not super well defined. It was easy to reach in and ask for the internal state of another component since they were running in the same process, and that led to some challenges down the line. The company became a lot more successful. The engineering team grew from just being a few number of backend developers to being a lot more. Many teams working on the same code base. And this whole process of scaling up the engineering team proved to be quite challenging using this structure. I think many companies follow this approach of trying to having autonomous teams that can deliver features independently without having dependencies on other teams. I think that's like a gold standard for many companies, and it can work well. But in a monolithic architecture, it's very easy to be bogged down with coordinating with other teams if you have a deploy cadence for the one application that might get in the way. And all these processes have to be some kind of homogeneous across teams. And it can be a problem. The failure modes are very simple, though. You can provide transactional guarantees within the monolith. So that's really the nice part. So in 2014, I moved to London, actually, and worked for a company called Halo. You may know them, the Get a Cab app. And it was very, very different, quite a culture shock to me, actually. They were already quite far in moving towards microservices. So instead of running all the processes in a single process, or the functionality in a single process, they would run each as separate services as separate processes. And when you deploy things, it would be a matter of saying, oh, I have this orange component, please run X replicas on this set of machines, rather than scaling up the number of processes on single boxes. So it was very different in many ways. And in the beginning, I was very frustrated with the way that if my component, let's say again orange, depending on the green, then suddenly it was an RPC call to access that functionality. And that means much more complex failure modes, or all the fallacies about the network timing out, so on and so forth. There was also no notion of transactionality. So suddenly you would have to handle being in these in-between states, or at least explicitly structure your applications. You wouldn't run into your data being in weird states. But after climbing this learning curve, it worked amazingly well on a very large team of engineers. Suddenly the engineers, the teams could really be independent. They would own a set of these services that they would both develop, deploy, and operate. So you would be responsible for the entire, these services across the entire spectrum. And if my team wanted to deploy some kind of new functionality, we could come up with an idea on Monday and have it in production and operate it ourselves by the end of the week. So it really led to a lot of innovation within the company and a lot of autonomy, ownership within the teams. So obviously this is just one anecdote, but I think it resonates really well with what other companies are telling about their experiences. Recently, Uber came out and said that microservices had been key to scaling up their engineering team, and I think they have more than any really seen massive growth issues scaling up a big engineering team. To make this very concrete, this is what a classic API might look like, microservices style. So you will have some kind of gateway that bridges between the outside world, the internet, and the internal world inside the microservice cluster, accepting HTTP requests and mapping them somehow to an RPC call to the microservice that should be responsible for handling this request. And that microservice might in turn depend on other microservices internally and make further RPC calls. And the response is that is then finally proxied back to the caller in the end. So this API can dynamically be extended by deploying new microservices and updating the mappings in the API gateway. So this really allows for a very malleable API. And obviously microservices can go away again, and you can really have a dynamic API. And what I wanted to do, my goal like a year back, was to investigate how can we achieve something like this using unikernels instead. And to understand why unikernels are appealing, let's take a look at how a microservice is typically deployed in the cloud. So the stack looks something like this. At the very top, we have the application. It might be very simple, a couple of 100 lines to 1,000 lines of code, easy to understand, easy to refactor or even rewrite. It's fairly simple. So it's running inside some kind of container, probably Docker, to provide isolation from other microservices running on the same machine. The container is running on top of some kind of operating system, let's say Linux, which is providing multi-process functionality. It's providing multi-user functionality, and obviously it's a stable hardware interface. So our application doesn't really care about which disk it's running on or which network card it's interacting with. Then we have the hypervisor, Zen. So from the cloud provider's perspective, you run multiple operating systems on the same hardware, which makes it much more cost-effective. And then finally, at the very bottom, we have the hardware. So we started with something that was very simple, right, or a small microservice, and we ended up with this very deeply layered stack, which is making things a little bit more difficult to understand, perhaps. So the idea of unikernels is how can we strip away the unnecessary layers, and instead of taking the traditional approach of computer science of layers, really, go back to do it from scratch. So the stack for a unikernel instead looks like this. So now your application is running directly on top of the hypervisor. And the question is then, well, how does this work? So the first responsibility of the operating system, which is crucial, is this stable hardware interface. But actually now we're all running in the cloud. There's not like a great diversity of hardware. We're all running on this virtualized hardware, which is totally homogeneous. So there's no need to have 10 different device drivers in your operating system. We can just write it up against this virtualized hardware. There's only one type of, and then that requirement goes away. The second is, previously we were running multiple processes on the operating system, but now instead we can just scale out by running multiple applications on top of the same hypervisor instead. Obviously, we still need to access the underlying hardware, and instead of having this operating system we interact with via system calls to read the disk or write to a network card, it's simply libraries now. So libraries are included explicitly in the application as needed, just as you would require something for serializing JSON or something. So what we gain from this in terms of security is a much smaller attack surface. We've literally gotten rid of millions of lines of unsafe code written in C, and we can replace it with code that can be written in safe languages like Camel, Haskell, and so on. There's no unused device drivers or other kinds of libraries included in the application unless it's explicitly required. So you won't have something lying around that you weren't aware of that can suddenly be used to exploit a security hole in your application. And finally, if somebody were to breach your application, there's no tools to aid the attacker at all. There's no basher, there's no, you can't LS things, there's no SSH or whatever to further exploit your application. In terms of complexity, well, it is a lot simpler. And just to give one example, we can look at how things are being scheduled. So on the traditional stack, we can have up to 3 layers of schedulers. So in your application runtime, you have a scheduler for green threads onto processes. In your operating system, you're scheduling processes onto virtual CPUs. And then in the hypervisor, you're scheduling virtual CPUs onto CPUs. And this 3-layered scheduling can actually have quite complicated interactions that can be hard to understand later. So in short, we've replaced this general purpose multi-user, multi-process OS with the minimal possible solution. Another way to look at this is how the address space looks like for a typical Unix process running this microservice and the correspondingly for Unikernel. So you have this strict separation between kernel space and user space in a Unix process. And crossing the boundaries between the two is costly. It's context switching. So every time you access the network, the disk, so on, then you're actually paying a price. Again, to reiterate, the kernel includes all the functionality that the application might possibly need, but not what it doesn't know what it really needs, because they are compiled separately, and you can't know when you're compiling your kernel unless you are recompiling it for every application what you actually need. So by comparison, in the Unikernel world, you only have a single address space where everything is running. And there's no distinction between kernel land and user land. So you're not paying the price of making system calls. You're just making regular library function calls. It only includes what's required by the application. So for example, if you're writing a DNS server that's not writing to disk, then you don't have anything for touching the disk at all. In terms of performance, this means that no context switching. It's trivial to achieve zero copy I/O. That is, normally when you're accessing the disk, then you're copying into kernel buffers and then kernel buffers to userland buffers. But when there's no such distinction, then it's trivial to achieve. Finally, you achieve whole program optimization, because since the operating system functionality is just a library, you can now inline code from those libraries into your application and optimize across the entire stack rather than when you have them compiled separately. Finally, unikernels, because they only include what they require, they're very small. We're talking kilobytes to megabytes for an entire Zen image, and they boot in milliseconds to be, instead of booting an entire operating system and then running your application on top. So far, I've talked about unikernels on a very general level, and for the rest of the talk, I'm going to be focusing specifically on Mirage, which is a unikernel written in OCaml. It's one of the most mature and oldest unikernels. And just to give you a flavor of what it looks like, this is a Hello World application. So as you can see, it has this main module, which is the entry point of the unikernel, and it has this argument, this console, which is of the interface console in capital letters. So it basically means at compilation time, it will inject a console of this signature, and it will either be for running on Unix or running on Zen, depending on how you've configured it. So basically, your source code is written once, and then at compile time, you decide, should this be a executable binary as the output, or should it be a Zen image? And there's actually further targets coming to Mirage now. There's support for KVM coming soon, so there's going to be a third target. And just to make it very concrete, these are the actual commands in the command line for running on Unix. And you might ask, why do you even have the Unix target? And that's for development. You write it, you run it on your local machine, test it, and so on and so forth. And then finally, at the end, you make a Zen image, and then you can run that in production. So now you have a basic understanding of microservices and unikernels. And the question is then, what do we need to replace these microservices with unikernels? And there are 4 requirements for such a platform, you might say. So obviously, we need some kind of RPC functionality so they can call each other internally in the microservice cluster. But to do that, we also need to know what services are out there and where are they. So that's what's called service discovery, which is basically like, what are the other members in my cluster and what functionality do they provide? Finally, we need to have some kind of deployment solution. If we want to, say, run X replicas of this service on a cluster, that's needs to be built. And once we're running this entire microservice cluster, we need to understand how is it performing, how is it running. Some kind of having insights into how your cluster is performing is essential for actually running this in production. So these are each massive topics. I'm going to consider the RPC one solved. We already have RPC libraries, more than plenty, and focus on the service discovery as the first step towards this goal. Once we have service discovery, we can still deploy things, although manually into the cloud, and we might not have insights with monitoring, but at least we can have a proof of concept that we can make a microservice architecture that works if we have service discovery and RPC. So for the remainder of the talk, I'm going to focus on service discovery. Okay, it doesn't. I have a picture. It doesn't like it apparently. The picture shows it's from the rooftops of Marrakesh, where the first Mirage hackathon was held this spring, and I was fortunate enough to be able to attend and be able to hack alongside some of the Mirage core contributors on actually making this solution. So we're just going to skip that picture. Service discovery. So we want to have this notion of who else is in the cluster right now and where are they. And the most straightforward solution would be to just introduce a centralized component. It might be a message bus like RabbitMQ, and that would solve all our troubles. We'd just communicate via that. But I would argue, we're trying to move towards unikernels. Why introduce centralized infrastructure that needs to be supported separately? And instead, we're going to focus on peer-to-peer solutions. That is, all the services are talking directly with each other. So the naive approach to this problem is for each of these services to ping all the other ones and ask, are you alive? And if you get a response back, they're still alive, and otherwise they're probably dead. So that works pretty well, but it doesn't scale up. This problem is generally called, or this types of protocols are called distributed membership protocols, and they should be evaluated against 4 criteria. Completeness, that is, if a node is down, then eventually a non-faulty node should find out. Speed is how quickly they find out that the other node is dead. Network load is how many messages or packets we're sending across the network. And the accuracy is the number of false positives. How often do we believe another node is dead when in fact it's not? So coming back to this naive approach of just every so often pinging another node and see if they respond, it actually works pretty well across 3 out of the 4 criteria, but network load, that one's really bad. Because the number of messages is quadratic in the number of members in the cluster. So if you have 1,000 nodes and they ping each other every 100 milliseconds, then you have 1 million packets across the network every 100 milliseconds. So it doesn't scale very well. So we need to find something better, some way to lower the network load while trying to retain all the other nice properties. And I looked into some of the existing solutions outside the unikernel world and in the literature, and I found this protocol called SWIM. So SWIM stands for Scalable, Weakly, Consistent Infection-Style Process Group Membership Protocol, so quite a mouthful. Basically, it's a peer-to-peer protocol over UDP with randomized heartbeating. So instead of heartbeating everybody, the nodes choose a random member to ping every interval with some gossiping on top. And I'm going to get into the details of that. There's a configurable ping interval. How often do you ask other members if they're alive? And it has 3 types of messages, ping, ACK, and pingrec, that I'm going to dive into in a little bit. And the basic idea is that we can trade off slightly lower detection speed for much lower message load. So that is, it's going to take slightly longer to find out that another node is down, but we're going to use a lot less packets, network packets doing so. It's linear in the number of members in the cluster. So to understand the protocol, I'm going to show 3 interactions that display how these 3 messages work in practice. So the first interaction is pretty simple. A pings C. The message has a unique ID for A. It has a sequence number, so it knows when it gets ACKs back, what is the responder ACKing. And let's say that C is alive, and it sends an ACK, and now A still considers C alive. What you see to the top right is basically the time ticking down for that particular interval. So it expects a response within that time. So that's the first interaction, fairly simple so far, ping ACK. The second interaction, we start over with the time, A pings C. But now after a certain amount of time, A says, hey, I would have expected a reply by now, but I haven't. Though note that the entire interval time hasn't gone yet. So it asks B for help and says, hey, could you ping C for me, please? And B now pings C. And C replies this time, and A now again considers C alive. So the basic idea here is that if there's some kind of trouble on the network, on the path between A and C, then we take an indirect route. And the number of helpers that A solicits to doing so is also configurable as part of the protocol. So the final interaction, A pings C again. We start over with the protocol time. We get the timeout again. We ask B for help, but we still don't get a reply. So now, at this point, we consider C dead, or A considers C dead. And now we get into the gossiping part of the protocol, because each node maintains a list of the most recent events that happened in the cluster. So every time a node dies, or when you for the first time receive a ping from another node, you consider them alive. That state is kept in each node, and they add that to the messages when they talk to the other nodes. So now when the next period starts of the protocol, A pings B, and now additionally says, oh, by the way, I think C's dead. And now B will update its own state, knowing that C is dead, and propagate that further. So now that's why it's called infection style. B is now infected with information that C is dead and will propagate that further to other members of the cluster. So this is the part that gives really nice, fairly nice guarantees with respect to how quickly other members learn that a node has come alive or a node has died. So what I've covered here is really the vanilla version of the protocol, and there's a number of extensions that we're in the disregard, but it might be nice. You might be sitting, oh, what about this use case or that use case, or how does it handle that? So I just want to mention 3. So the first is you can increase accuracy by, instead of immediately assuming a node dead, marking it as a suspicion, and then you can later learn that the node was actually alive. So that decreases the rate of false positives. Secondly, in the vanilla protocol, when you join a cluster, you just ping a member, and then you're a member of the protocol, but it actually takes time for you to build up the entire state of who else is there. So a natural extension is to get a full sync when you join a cluster. And the final one is some kind of metadata. So right now, we can't distinguish between the nodes that are part of the cluster. What kind of functionality do they provide? And that's actually essential for our service discovery mechanism. So when you join a cluster, you say, oh, and by the way, I provide the login service or the get a cap service or whatever. None of these extensions really change the fundamentals of the protocol. So just so you're aware that it's there. So now I hope you have a grasp of what the protocol works like, and we're going to look a little bit at how it's implemented and some learnings from doing that. So these are the messages, the types of the messages being interchanged on the network. So an address is an IP and a port. There are 3 message types: ping, ping, ACK, and pingreg, where pingreg has additional knowledge of who to ping. The state is either dead or alive, and then a message is finally a sequence number, which uniquely identifies the message, a message type, and a list of gossip saying this node is dead or alive. And if we look at how the nodes individually handle such a message coming in, we can think a little bit about immutability and purity and side effects. Now, OKernel is a functional language. It promotes immutability, but it doesn't force your hand. You can mutate state all you want. You can have all the side effects you want, write to the network, write to disk, do timeouts. So there's really a matter of choice in how to implement this and whether you want to go pure or not. And I want to explore a little bit what does it look like if you want to make something that's actually pure in terms of side effect free and not mutating data, and what are the implications. So our starting point is the typical imperative solution. When you handle a message, there's the state of the node, you get a message, and then you just return unit. Because you're mutating data, you're writing directly to the network. It's not, you can't really tell from this type signature that all this stuff is happening. So let's say we want to get rid of the mutability part. We want to make it such that the data is mutable. Well, now, instead of returning unit, we return the new state of the node. So we've gotten rid of, we now have immutable state, but we're still writing to the network, and we're still setting timers. We need to figure out if other nodes haven't responded in time. So how could we approach this problem of, for example, getting rid of writing to the network? Well, now instead of just returning a state, we also return a list of actions that we would like the caller to take. And the actions are, please send a message to this address, and here's the message. So that's the send message you see up here. So now we're no longer touching the network. We're asking the caller to do that for us. But we're still setting timers. We're still not, the timeouts are not part of this model. And the final version of trying to handle this purely looks like this. So now we have an opaque timer type, and the actions that we return from our handle event function is now, it can either be please send a message, or it can be please set a timer. And the events we receive are not only messages, but also something timed out. And it's this particular timer that you asked me to handle. So at this point, it's totally pure, it's immutable, it's side effect free. And I think, you can argue in terms of readability, the state transitions are really explicit in the program. But I think that's all a matter of taste. Where it really becomes a net benefit that you can't really argue about is how you can use this pure core in different contexts. So, for example, you might wrap the pure core in something that does synchronous I/O. It's straightforward. It might interact well with your program that's already using synchronous I/O, but you can also wrap it using asynchronous I/O, or you can mock the network and mock the time for testing, or you can have an effectful wrapper which is suitable for Mirage. So I think that's really a benefit that you can't argue about in the same way, the readability and should you distinguish between separate I/O and core logic. So the effectful wrapper sends events to the pure core sends the actions back, and it's the responsibility of the wrapper to actually interact with the network and set timers. The pure core has a little bit complicated interface. These are mostly types you've seen before. So you can ask the pure core about what are the members of the cluster, please start failure detection, please handle an event. And it looks really complicated. But when we wrap it in an effectful wrapper, the interface is actually really trivial. And this is what it looks like for Mirage. So you can start it, you can stop it, you can join a cluster, you can ask for the members. So we have this distributed probabilistic algorithm lying at the core of our microservice architecture. And it's really essential that it works. And by nature, it's quite tricky to get confidence in the solution. The first approach will probably be unit testing. I started like this. I wrote some scenarios down. I saw that it acted as I expected, and it worked fairly well. I think the program was already, the design was already set up for success in terms of it was easy to mock network in time, so the tests were fast and easy to write and so on. But it only goes so far. Let's take an example. So there's an initial state where we have A being part of the cluster. It's tied up to a mock network. And then we have this event in our test scenario where B joins A, and then we wait for a second, allowing them to gossip a little bit. And then C joins A, and we allow them to gossip a little bit. And then we let A fail by disconnecting A from the mock network, and we let them gossip again. And then at this point, we know how the protocol works. So after these steps, we should verify that B knows C is alive and C knows B is alive. And the reason we know that is we know how the protocol works, right? But writing down all these scenarios and testing them each individually only goes so far. Even if I did 100 scenarios, it's minuscule compared to the number of states the cluster could really be in when you look at a large number of nodes. So is there a different approach to solving this problem of gaining confidence in the solution? And the basic idea is if we can, for each of these steps, like join BA, wait 1 second, can have a model of the world, an idealized model of the world, a much simplified model of the world, then we can, instead of manually writing down test cases, let the computer generate test scenarios for us. So as a very simple example, let's let the model of the world be the set of nodes that are currently alive. And in the initial state, A is alive. So for each of these events, we need to figure out how to update the model. So when B joins A, B should become part of the set of alive nodes. So we simply add it to the model, and at the same time, we run the code against the mock network and so on. Then when C joins A, again, now C is part of the alive node set. And finally, when A fails, we remove it from the alive node set. And instead of manually now verifying that the world is in the state we expect, we can use the model of the world to verify that the world is in that state. So the model says that B and C should be alive, so B should consider C alive, and C should consider B alive. And so an overview code-wise of this looks something like this. We have a number of events. A scenario is a list of events. We have the state, which is our model of the world, and a list of our pure logic. And if we can write a step function that takes the state and an event and gets us a new state, that means we can execute a scenario by simply executing the steps one by one. And if we can write a validate function that looks at the state and compares our model of the world with the actual world, then we can basically let the computer write any number of test scenarios and validate that the algorithm works as expected. So this also works for different models. This model was quite trivial. It was just the set of alive nodes, but we could also have the model be a graph with the latencies between the nodes. And then suddenly we can start verifying that it handles network latency correctly or packet loss or something else. Obviously, the more complex your model becomes, the more you need to ensure that there's not a fault in your model, but actually in the code. So at this point, we can actually build the architecture I showed earlier with the REST API, build microservice style. We have RPC. So we assume we have RPC to call between the nodes. We have our service discovery algorithm, our gossip algorithm for determining who else is in the cluster and what functionality do they provide. We can deploy, although in a manual fashion for now. That's work to be done, how to deploy Unikernels in a smart fashion. And monitoring is, for now, left as an exercise or undone work. So it needs to be done. But I hope I've given you a taste of, first of all, how microservices can be interesting for scaling up an engineering team, how unikernels are not only simpler literally, but also conceptually, and can provide gains in terms of speed and security, and how this all fits together, and a little bit about the road forward. So if any of you is interested in working on this, reach out to me. The code is on GitHub. And otherwise, thanks very much for listening.
So we have about 3 minutes for questions, so let's see some hands.
Hi. There's a product from HashiCorp called Surf, which does implement Swim. So I was just wondering, in your testing, where you're basically proving an equivalence between your implementation and your model, did you consider trying to prove that same equivalence between your implementation and Surf from HashiCorp?
Yeah, so you're totally correct. Surf does implement the same algorithm. And the reason it's not used here is basically it's not unikernel compatible. I haven't tried running this against what they've done. They have written Surf in a direct style, impure imperative. So I think it would be a lot harder to go and do the same kind of verification. Maybe you could restructure the program and then you could run use the same approach to verifying that stuff. But I think it would be a lot harder.
Hi. I had a question about security. Is that an issue in this sort of architecture? And if so, how do you deal with it? And if not, why not?
For unikernels?
For unikernels, the sort of architecture that you're proposing, yeah.
So I would argue that security is improved compared to the traditional style of writing applications. So it's basically the benefits are a lot less third-party dependencies, which means a lot less code, with potential exploits. It's also a matter of if your application is exploited, then there are really no tools to aid the attacker in going further. There's no bash shell. There's no.
I suppose I was thinking at a higher level. If I manage to put a malignant agent in there who is broadcasting to everybody, look, I can provide you with this. How do you ensure that you're actually that the what a service says it's going to do is actually what it's going to do?
So it's in terms of Swim.
In terms of a microservices architecture.
Right.
If I insert
Okay. So once you are inside, if you do manage to get a malicious actor inside the cluster, then I think in general, yes, you can do bad stuff. Obviously, you shouldn't be able to. Your microservices should verify that the requester only gets permission to do what the caller has permissions to do. So if you have some kind of authentication system, and you should, then you should authorize the action they want to take against that.
Okay, so I guess you're assuming security guarantees from your cloud provider and from Mirage and so on that will.
If I understand the question correctly, this is application level security, not something that's explicitly provided by by Mirage,
Right.
or Unikernels in general.
Okay.
And we're out of time, so yeah. Let's thank the speaker again. Thanks.